Hello everyone, my name is Raful Azam. Welcome to the next tutorial. Today we are going to see week 5 assignments. So in this particular week 5 assignments, basically there are three exercises which we need to complete. The first one is sigmoid gradient.m, second one is rand initialize weight.m, and the third one is nn cost function.m. So coming to the first one, which is sigmoid gradient.m. So here what we are going to do here, we just want this g is nothing but it's a differentiation of, or you can say partial differentiation of sigmoid function. So this function is going to return what? Partial differentiation of sigmoid function. So if I can show you here, obviously this is the sigmoid function which we know 1 divided by 1 plus e power minus z. Now we just want to do the partial differentiation of this g of z with respect to what? Z. Okay, so this can be written as obviously how? E power z divided by 1 plus e power z, right? This can be, now we want to do the differentiation of this e power z divided by 1 plus e power z with respect to z. So obviously this is in the form of u by v. So in u by v, we know we need to take v outside and then differentiating u, then minus u taking outside and differentiating v divided by v square. So when you differentiate, what it will become? It will basically become here 1 plus e power z, that is taking denominator, and e power z differentiation in e power z itself, and then here minus, and then taking the numerator, and here 1 plus e power z differentiation again e power z itself, divided by 1 plus e power z whole square, right? And this will become e power z plus e power z, and that will get cancelled, so just the remaining will be e power z divided by 1 plus e power z whole square, right? And I can write this as a like this. So that is e power z divided by 1 plus e power z. If I take it common, so the remaining will be just 1 divided by 1 plus e power z, right? And this can be written as e power z divided by 1 plus e power z into 1 minus 1 minus e power z divided by 1 plus e power z. If you do, you'll getting the same, you will get the same. And this is nothing but what? This is our sigmoid function, right? This values a sigmoid g of z. So basically what we are getting here, g of z into 1 minus g of z, right? So this is the nothing but the partial differentiation of sigmoid function. So this is what we want to implement here. So the sigmoid g is nothing but what we are going to sigmoid of z into, as it is z can be anything, right? It can be matrix or vector or scalar. So we want to do for each element of that particular matrix, so we are writing dot into 1 minus sigmoid of z, sigmoid of z. So this is what we got, sigmoid of z into 1 minus sigmoid of z. Now coming to the next, so here what we want to do, basically we want to randomly initialize the weight of our L in and L out, right? Where L is nothing but the incoming connection and L out is nothing but its outgoing connections. Okay, so what we are going to do, we have just initialized W is equal to zeros of L out comma L in. So this is the zeros of weight we have initialized. Now we just want to return this W correctly. Okay, so here to initialize randomly, what we are going to do, we are just going to take epsilon init is equal to 0.12 and w is equal to this. So why we are basically taking this, if I can show here, see it is in random initialization, it is recommended to use, they have told that we need to use epsilon init as 0.12. So that's the reason we have used this, and we want our values to be ranged from minus epsilon init to plus epsilon init. So in order to get the values from minus epsilon init to plus epsilon init, we are just writing w is equal to rand of L out comma 1 plus n in. So this rand of L out comma 1 plus L in, what it will do, it will just initialize the matrix. It will create a matrix of this size. So suppose if it is 10 comma 11, so it will create a matrix of 10 comma 11, and when you multiply into 2 and then epsilon in it, and again later will when we subtract epsilon in it, we'll get all the values which is ranging from this to this. So that's the reason we are writing this. So I hope it is clear why how we are initializing this random initialization. Now coming to the next one, which is n cost function dot m. So here what we want, basically there are totally three parts which we want to implement. So in the first part we want to this, what we want to do, so we want to do feed forward the neural network and return the cost in the variable j. After implementation part 1 you can verify. So this we just want to return a cost function here in the first part. In the second part, what we want, we implement the back propagation algorithm and compute the compute the gradient theta 1 and theta 2. So here we want to compute the gradient theta 1 and theta 2, And in third part, what we want to implement regularization with the cost function and gradients. So these are the things which we want to implement. Okay, so what are the parameter which we are passing? So here obviously we are giving the number of parameters, and then this we are giving what are the, so this number of parameters need to be converted back to the weight matrices. We need to convert this nn parameter to weight matrices. Okay, and this input layer size we are giving whatever the input layer size, then hidden layer size, and we are giving the number of labels and then x comma y, this is the output, and lambda for regularization. Okay, so these are the terms which are passing. So after that, what we did, we just reshape our theta 1 and theta 2, and m is nothing but the size, and we are initializing the variable j and theta 1 gradient and theta 2 gradient. Okay, these are the two variable which we want to return. Now coming to here, so if I can explain here, say this is the neural network, right? So suppose if this is the theta 1, so theta 1 is the weight for it, and this is the theta 2 which is the weight for this. Okay, and these are the x is nothing but the input. We are just considering everything in the form of matrix, so x is the here input, or you can say the training example here. So here what we have done, we have just taken this x, but the thing is we are just going to add 1 in the first column. Okay, so that is our x, and after taking the x, we have just initialized that a1 is equal to x. It is same as the in my previous tutorial in week 4. I've explained this all, how we can implement this. So here just a1 is equal to x, but once again I'll repeat. So here we have taken input a1 is equal to x. Now we are calculating what is the z1, z2. Z2 is equal to a1 into theta 1 transpose. That is the output over here in this hidden layer. So what is the output here we'll get? So obviously input into this theta 1 will give you the output, and then we are going to pass it to activate this activation function, which is the sigmoid. So we are passing it to the activation function this output, and after that again for the second layer, right, whatever the output we are getting at the second layer, that will act as the input for third layer. So again in the second layer input output also, we are just going to add 1 in the first column and then multiply it to the theta 2, and then we'll get the output for this output layer, right? So a2 is equal to, we have added 1, and then in a2 1 in the first column, and after that what we are doing, just 3 is equal to a2 into theta 2 transpose. So this is the output for third layer, that is our output layer, right? And then again we are passing to the sigmoid, that is the activation function, and we'll get a3, and that a3 is nothing but what, our hypothesis, or you can say our predictions, right? A3 is nothing but the output which it is going to predict. Now what we have done, we have just taken this y, that is the output unit, in y back, and now we are writing the cost function. So here the cost function is same as sigmoid, only the thing is what we are going to do, we are going to, as we have 10 levels, right, or the levels can be anything in neural network. See, if I can show you here, there are totally 3 layers, so we need to add the output over all these 3 layer, right? So that's the reason we are going to add one more sum here, one more summation, or else it is the same as the sigmoid cost function, sorry, same as the logistic regression cost function. So what was the logistic regression cost function? It was 1 by m, and then sum of minus y, this minus y, obviously this. So here y we have taken as a y back, the minus y, and log of this hypothesis prediction minus of 1 minus y into log of 1 minus h of x. And just this one more sum is nothing but what it is doing, it is just adding all the output over the all the this all the labels. So as we have totally three layers in this output layer, so we are adding over all these three. Okay, now coming to the implementation of back propagation. So in back propagation, what we are going to do, again the same thing will repeat. Just we are first calculating here z2, that is the output for second layer, and after calculating, passing to the sigmoid, that is the passing, we are passing it to the sigmoid function, and then again we are taking the z3. So this is again the output for the output for the our output layer, and then we are passing it to the sigmoid, that is the activation function, and we got a3. And again we are initializing y back is equal to y, that is nothing but the, we are considering again y back is equal to our outputs y. And now the thing is, we want to in back propagation, what we do basically, after getting the output here, okay, suppose we got the output h of x here, now we are going to calculate what is the error at this output layer. After getting the error, we'll start doing the back propagation. Okay, so we'll differentiate this error, and we'll try to get what is the error at the second layer. And obviously in the first layer we don't try to get the error, because this is the input layer itself. So we'll try to get what is the, if there are more than three layers, Then we also use to calculate the errors between all the layers, or you can say all the for all the hidden layers. Okay, so now here what we are doing, we are just calculating what is the error a3 minus y back. So this a3 is nothing but whatever the output we got. Okay, and then we are just subtracting from the actual output which are given in the training example, and we got the error. Okay, error at the third layer. Now after getting the error at the third layer, to get the error at the second layer, what is the way? So if I can show to get how we can get the error at the second layer. So see here, to calculate the error at the second layer, if we do theta 2 transpose whatever the value here, theta 2 weight here, so that transpose into error at the third layer, and we do this for all the elements of matrix into, and this g transpose of z2. So this z2 is nothing but the or values that 1 by 1 plus e power x, right? 1 by 1 plus e power minus x, and we are just passing this value. And I already showed this values, this g of z, that is sigmoid gradient is equal to what we have done also in this implementation, that sigmoid gradient is equal to sigmoid z into 1 minus sigmoid of z. So that's how we can calculate the error of the second layer. So just delta 3 into theta 2, and we are going to do this element wise multiplication, and here this sigmoid of z2, and this is the just one we are going to add in the first column. So as we are adding one in the first column, and we are not going to take that first column, right? So we are just taking that from the second to end. So we have taken delta 2 is equal to from second to end, because in gradient when we are going to differentiate, we are not going to differentiate the bias term, right? So that's the reason we are going to take from the second column. So after getting delta to this, so we just want to calculate theta 1 gradient. So theta 1 gradient is nothing but 1 by m into delta 2 transpose into a1. So this is the way to calculate the theta 1 gradient. If I can show here, see this yeah. So basically how we can get this this is nothing but this uh, the partial differentiation of cost function. So that is nothing but 1 by m and delta ij l. So this delta ij is l is nothing but what, delta ij here this is 0. So basically this is equal to delta l plus 1 and a l transpose. Okay, so this is how the way we can calculate. If you multiply the error term with the a value, so you'll be getting the differentiation, partial differentiation. Okay, so that's what we are doing. We are just doing the multiplication 1 by m to get the theta 1 gradient, 1 by m into delta 2 transpose into a1. So here a1 is nothing but the input, right? And theta 2 gradient is 1 by m delta 3 transpose into a2. So a2 is the output for the second layer, right? So this is how we can calculate theta 1 and theta 2. Now coming to the third one. So in third part, what we are going to do, we are just going to implement the gradient with regularization. Okay, so here we are going to just add the regularization term. So the regularization term is nothing but lambda by 2m into sum of theta 1. Obviously there are two thetas now, so we need to add all the thetas, and we are going to take only from the second one because the first one is the bias term. Okay, so this is the theta 1 and theta 2, and we are going to add this sum over all the layers, like from the input as well as for the hidden layer, and here this is for hidden layer as well as for the output layer, and then we just write lambda by 2m. If I can show here, so see here, we are just going to, this is the regularization term. It is lambda by 2m. We are going to sum over the input layer as well as hidden layer, and then we are going to sum over the hidden layer as well as for output layer. So this is the bias term which we are going to add. So that's what we have added here, regularization. And now the cost function will become just cost function plus regularization term. And after getting this, what we want to do, we just want to find again the theta 1 regularization, like what is the gradient after adding the regularized term. So just the thing is, whatever we got theta 1 and theta 2 plus whatever the differentiation, right, or partial differentiation of this regularized term. So to get the partial differentiation of a regularized term, if we differentiate this regularized term, what we'll get? We'll just lambda by 2m, and here we are just going to add zeros in the first column, and then we are taking the theta from obviously from second till end, and again the same thing for theta 2 also, we are taking the theta 2 from second to end, and this is the what we got the differentiation of regularized term. And after that finally we can write that theta 1 gradient is theta 1 plus theta 1 gradient regularized, and that's how we get the theta 1 theta 2, and this is the regularized term, right? So once we got this, after that what we'll do, we'll just unroll the gradients. So this is the gradient which we are going, which is it will unroll, and again this values will be passed to the main method. Or you can say again this values will be passed to here nn parameters, and that nn parameters is again going to reshape in the form of theta 1 theta 2, and this keep on happening. So that's all about today. If you have any doubt, please comment down below. I'll be happy to answer. And if you like this channel, please like, share, and subscribe. Thank you.